Hello everyone. Today I'm going to talk about the modulation and detection of AM radio. The AM radio has a simple structure and is easy to understand. It's used in communication and radio broadcasting. Here is an AM radio transmitter, run by battery. On the transmitter, there is a local oscillator that can produce a frequency in the range of 520 kHz to 1600 kHz. And that's the carrier frequency or transmitter frequency. This is the modulating signal input. This signal modulates carrier frequency, producing AM signal. The signal is then amplified and transmitted out via this antenna. The input modulating signal can be an analog or digital signal we want to transmit to receivers. Here is an AM radio receiver antenna circuit. The antenna includes two coils, a big coil and a small coil. The big coil is connected in parallel with a variable capacitor, forming an LC-tuned circuit. The small coil is the antenna signal output, and is connected to the scope channel 2. When the receiver antenna circuit is in tune with the transmitter frequency, the antenna catches radio signal from the transmitter. Now we turn on the transmitter. In this experiment, we adjust the transmitter carrier frequency to about 800 kHz. On the receiver circuit, I turn the variable capacitor to catch the radio signal transmitted from the transmitter. We now caught the radio signal. Let's see what signal it is. This is a sine wave signal. We can read 803 kHz here. If we look at the signal in a bigger time window, the signal looks like this. The inside is a carrier frequency 800 kHz sine wave. The amplitude of the signal is flat and unchanged. The outside border is the envelope of the signal. Now we input the modulating signal to the transmitter. I first will try with the sine wave signal. Here is a signal from this signal generator. This signal is a sine wave, frequency 1 kHz, and the amplitude 200 millivolts. Now we start letting the modulation signal modulate the carrier frequency. I'm increasing the modulation index. As you may know, the AM is the abbreviation for amplitude modulation. This input signal modulates amplitude of the carrier frequency, making the envelope of carrier frequency to have the shape of the input signal. If the input modulating signal is a voice signal, we will see the envelope of the carrier frequency changing as the voice signal. And this signal is the amplitude modulated signal, as we can see the amplitude of the carrier frequency changing up, down like the input signal. Now we will try with other modulating signals. Now the modulating signal is square wave, and we see the envelope of the carrier has the shape of square wave. This is a ramp signal. Now the modulating signal is a triangle wave. And we can try to change the modulation index by adjusting this knob. Now we go back to the sine wave signal. The AM signal is in the time domain. Let's see the AM signal in frequency domain. In the frequency domain, we see there are three dominant frequencies. The middle one is 800 kHz, the one on the right is 801 kHz, and the one on the left is 799 kHz. If you want to know more about the formula of AM modulation, Here is the block diagram of the AM transmitter. This is the modulator or the mixer. This is the local oscillator, generating carrier frequency. Our carrier frequency now is 800 kHz. This is the modulating signal input. The modulating signal is now 1 kHz sine wave. When modulating signal and carrier frequency signal are mixed, it will produce the AM signal output. Here is the formula of the mixer or modulator of AM signal. The AM output signal is then amplified and transmitted via the antenna. If the frequency of modulating signal is F1 and frequency of carrier signal is F2, then there are three frequencies at the output signal. They are F2, F2 minus F1, and F2 at F1. Assume the modeling signal is 1 kHz sine wave with amplitude 0.5 volts. Carrier signal is 800 kHz sine wave with amplitude 1 volt. And when we replace the modulating signal and carrier signal into this formula, we finally got three frequencies. The first one is 800 kHz, the second one is 799 kHz, and the third one is 801 kHz. At the transmitter, we have 1 kHz sine wave signal mixed with 800 kHz carrier signal, producing AM signal, and transmitted out. The antenna receiver circuit receives the radio signal, and it's shown on the scope. When looking at the signal in the frequency domain, we see three frequencies: 800 kHz, 799 kHz, and 801 kHz. Now we go back to the time domain. Here is AM signal. Inside here is 800 kHz, and the envelope is 1 kHz. I'm now going to feed in the transmitter the voice signal. Now the modulating signal is the voice from an online audiobook. The voice signal modulates the amplitude of the carrier frequency. The envelope of the carrier changes like the voice signal. Okay, I briefly talked about the AM modulation and some modulating signals. Now I'm going to talk about a receiver circuit. The signal output from the antenna will be fed into an AM detection circuit, and then to an audio amplifier, and to a speaker. Here is an AM detection circuit. I will feed the signal output from the antenna to the input of the AM detection circuit. The circuit will detect AM signal and filter out the carrier frequency. At the transmitter, if the modulating signal is an audio signal, we get back the audio signal at the output of the detection circuit. The detection circuit includes a diode and a resistor and a low-pass filter. The low-pass filter will remove the carrier frequency out. Before the signal from the antenna goes to the detection circuit, the signal is amplified 100 times, making the signal large enough for the detection diode to operate. Now we feed antenna signals into here and supply power for the amplifier. This is a higher frequency amplifier. I'm connecting the output of the antenna to the input of the detection circuit. Here the oscilloscope will probe on two more points. Point A is the signal amplified 100 times. Point B is the signal after it goes through the detection diode. Currently the capacitor is left opened. I want to isolate the low-pass filter, so there is no low-pass filter in the circuit. On the scope, there are four signals. The top one is a signal from the signal generator, 1 kHz sine wave. Next is the signal from the antenna output, and this is the output signal from the high-frequency amplifier. As we can see, the signal output from the antenna is about 50 millivolts peak to peak. The signal after the amplifier is about 3 volts, and that's the signal at point A. And here is the signal at point B, where the signal passes through the diode detection circuit. When the signal goes through the diode circuit, we see the bottom half of the signal is cut out, left over the top half signal. Inside of this condensed signal is the 800 kHz frequency, and the envelope is the 1 kHz. Currently, there is no low-pass filter in the circuit. We now connect the filter capacitor to the circuit. We will see the high-frequency 800 kHz is filtered out, giving out a 1 kHz sine wave at the output. Yeah, when the capacitor is connected, the output signal becomes a sine wave signal. Now we can try to adjust the modulation index. Now try with square wave modulating signals to see how the output looks like. Now try with a triangle signal. Now we solder the capacitor to the circuit. Change back to sine wave signal. This is the knob to control the modulation index. When increasing the modulation index, the amplitude of the output signal is higher. When decreasing the modulation index, we see the amplitude of the signal lower. Currently, we have the diode mounting in this direction. This AM signal is chopped off the bottom half. If we change the direction of the diode, the AM will be chopped off the top half. And now I reverse the diode so we can see. I'm changing the diode direction. This diode is the germanium type diode. Its forward voltage drop is only about 0.3 volts. If we use another silicon diode, its forward voltage drop is about 0.7 volts. And we need the amplifier to have a higher gain a little bit. I now remove the filter capacitor to see the signal. As you see earlier, the diode was mounted in another direction. The AM signal is chopped off the bottom half. Now we change the diode direction. The signal is chopped off the top half. Connecting the filter capacitor, the high frequency is filtered out, yielding 1 kHz sine wave signal output. Placing a diode in this direction or reverse direction, the signal output is 180-degree phase different. However, the sound we hear is the same. Here is a simple audio amplifier using a LM386 chip. The output is connected to a 8-ohm speaker. At the input front end, I have a variable resistor to control the sound volume. Now we will connect the output of the AM detection circuit to the input of the audio amplifier. We can actually hear the audio signal at this point, but it is very weak. Using headphones we can hear the audio from this point. We want to hear louder from a speaker. We need an audio amplifier. Okay, provide 5 volts to the audio amplifier.
Oh, okay.
We have 1 kHz signal from the signal generator. The signal mixed with carrier frequency and transmitted to the receiver. The receiver receives the radio signal, amplifies it, detects AM signal, and send to the audio amplifier and to the speaker. This is 1 kHz here. Now I'm going to change the frequency on the signal generator, then see how it is at the speaker. Now we feed the audio signal here.
Cho qua chuyện. Chị Hường, có lẽ sợ tôi đủ thân dỗ dành. Người ta nói gì cũng mặc kệ, cưng không phải con nuôi của nhà này đâu.
I've shared with you the AM radio signal from the transmitter to the receiver. I'd like to talk a little bit about this transmitter. This transmitter is different with regular AM transmitter of a broadcast radio station. This transmitter can only transmit magnetic fields. The transmitter of a radio broadcast station can transmit electric and magnetic fields. The electric field and magnetic fields combined can bring the carrier frequency to very far. And the transmitter of a radio station needs a very tall antenna for AM band. This transmitter can only transmit magnetic field, and the longest distance it can reach is about 1 meter. Even though it uses only the magnetic field, it is able to deliver a full signal or data from a transmitter to receivers. And at the receiver, even though the radio station transmits electric and magnetic fields, they are perpendicular and propagating in space. The receive antenna can only receive the horizontal magnetic field component. The magnetic field component goes through the ferrite core, causing resonance frequency on the LC tuned circuit, and radio signal can be received at the output of the antenna. I've talked a little bit more about the AM radio antenna, and that concludes my presentation today. Thank you all for watching.